Hello dear colleagues. Today I want to present you the article studying the strength and damageability of composite element in looped metal composite joint under tensile loading. The article presents the result of computational and experimental studies of the strength and damageability of connecting composite part in a metal composite joint of isogrid and anisogrid structures made of polymer composite material under tension. The assessment of the minimal cross-section area of the connecting parts was performed based on design calculations taking into account stress staining during extrusion of the excess binder. The onset of failure in the contact zone with the steel element of the metal composite joint was predicted based on experimental studies using model samples. A comparison was made between the calculation results for the tensile loading diagram, considering the physical nonlinear behavior of composite material in the joint zone, and the readings of strain gauges after testing the metal composite joint. Damages and deformation of the connecting composite part under the tensile load was imaged using acoustic microscopy. The slide shows a composite structure and metal composite joint. To calculate the total strength, characteristic and parameters of the minimum loop cross-section based on the given microfiber properties, the calculation scheme with compressed package shown in the figure was adopted. The rule of mixtures based on the isostrain assumption for estimate the longitudinal stiffness modulus and tensile strength of unidirectional package of the loop was used. In general, the load displacement dependence is linear. The deviation of the load displacement relationship from linearity was revealed when the load exceeded 260 kilonewtons. This corresponds to the initial formation of damage, including plastic deformation of the bolts securing the metal composite joint and the destruction of composite material in the loop. The stress-strain dependence was measured by load cells number 1, 2, 4, and 5. A weak nonlinear nature of the stress-strain dependence with an increase in structural stiffness was revealed that confirms the high strength of the metal composite joint structure developed. A comparison of the experiment with the nonlinear numerical solution shows satisfactory agreement. The differences between theory and experiment is explained by the combination of physical and geometrical nonlinear behavior of the loop. At low tensions, it is related to measurement errors. As tension increases, fibers with the loop became straighter, and stiffness increases too. The following tension leads to geometrical nonlinearity, then stresses at external and internal surfaces of loop are getting equal. So stress on the external surface, then the strain gauges is located, increases. Geometric parameters of composite element in a loop metal composite joint were obtained, providing the required tensile strength. This was verified using finite element method and impulse acoustic microscopy. Results of static tensile test showed satisfactory convergence with numerical calculations considering nonlinearity. Acoustic microscopy confirmed that carbon fiber structure wasn't damaged at maximum design load. Deformation of composite element was accompanied by 1.1 times structural compaction in contact zone of the joint. Thickness of the loop changed from 6.4 to 5.8 millimeters. Figures on the right. This in turn resulted in slight migration of technological defects. The binder was squeezed out in the most stressed joint area. No other damage was detected as the applied stress was nearby 30% of the calculated strength limit. This approach can be useful for designing products based on lattice composite structures, which include metal composite joints and whose reliability is highly demanded during operation.